Our solar system feels familiar. It is our home. We know its landmarks, the scorched surface of Mercury, the majestic rings of Saturn. We have sent robotic emissaries to almost every major world, mapping their craters, tasting their atmospheres. The Sun, our parent star, illuminates this family of planets, yet, beyond the orbit of Neptune the light begins to fade. In the vast frozen twilight our map becomes uncertain. This is the frontier, strange, immense, and mysterious. The edge is not empty, a sprawling wilderness teeming with icy bodies. This region is the Kuiper Belt, comets, dwarf planets, Pluto. These objects drift in the profound cold. They take thousands of years to orbit our distant sun. For a long time we thought it a quiet graveyard of debris. But the more we look, the more we realize something is stirring in the darkness, something immense and unseen, betrayed only by faint whispers carried across the void. Imagine standing on the surface of one of these distant worlds. The sun would be little more than an intensely bright star, its warmth barely perceptible. The silence would be absolute, the darkness almost complete. Yet you might feel a pull, a gentle but persistent nudge from something other than the sun. Astronomers are feeling this too as they study the most remote objects we have found. These tiny worlds are not moving as they should, their paths are skewed, their orbits are strangely aligned, as if an invisible shepherd is herding these icy sheep in the dark. This is where our story begins, a detective story on a cosmic scale. The crime scene, the edge of the solar system, the victims, a handful of icy worlds with disturbed orbits, and the suspect is a ghost. A giant hidden planet, perhaps 10 times Earth's mass, lurking in the deep freeze. We call it Planet 9. Its discovery would rewrite our story of the solar system. So why do we think there might be another planet out there? The idea is not new. The history of astronomy is filled with stories of planets discovered through their gravitational influence. In the 19th century, astronomers noticed that Uranus was wobbling in its orbit. It wasn't following the path that Newton's laws of gravity predicted. Something was pulling on it. This gravitational disturbance led directly to the discovery of Neptune in 1846, found almost exactly where the mathematics said it should be. It was a triumph of theoretical science, proving that we could find a world not with our eyes, but with our minds, by observing its effect on its neighbors. Today, we are seeing a similar story unfold, but on a much grander and more mysterious stage. This time, there is no single planet being tugged. Instead, we see a whole collection of small, icy bodies in the distant Kuiper Belt, all moving in a strangely coordinated fashion. These objects are called extreme trans-Neptunian objects, or ETNOs, and their orbits are truly bizarre. They are all tilted in the same direction and swing out to one side of the solar system like the hands of a clock, all pointing to the same hour. This kind of clustering is incredibly unlikely to happen by chance. It is a pattern screaming for an explanation. Think of it like this. Imagine a calm pond with a few leaves floating on the surface. If you saw all the leaves suddenly drift towards one side of the pond, you wouldn't assume it was a coincidence. You would look for a cause. Perhaps the wind is blowing, or maybe something large and unseen is moving beneath the water, creating a current that herds the leaves together. Astronomers are doing the same thing. They see these tiny, icy worlds being herded into these peculiar orbits, and the most straightforward explanation is that a large, unseen object is moving through the depths of our solar system, its gravity shaping their paths. This is the essence of the case for Planet 9. It is an inference, a conclusion drawn from the subtle gravitational clues left behind in the orbits of these distant travelers. The planet itself remains unseen, a shadow lurking in the cosmic dark, but its gravitational signature, its ghostly fingerprint, appears to be imprinted on the very architecture of the outer solar system. The evidence is not yet definitive, but it is compelling. It suggests that our planetary family might be larger and stranger than we ever imagined, with a massive sibling hiding just beyond our sight. Let's look more closely at the evidence. The clues are written in the language of orbits. The paths that objects take through space are governed by gravity, primarily the immense pull of our sun. For most planets and asteroids, these paths are relatively flat, lying on a plane called the ecliptic. It's like a cosmic dinner plate, with the sun at the center and the planets orbiting near the flat surface. But when we look at these extreme trans-Neptunian objects, we find something astonishing. Their orbits are not flat at all. They are tilted dramatically, sometimes by 30 degrees or more, rising high above the ecliptic, plunging far below the ecliptic. These tilted orbits are all tilted in roughly the same direction, a collective alignment that is profoundly odd. If their orbits were shaped only by the known planets like Neptune, you would expect them to be scattered randomly. Some would be tilted up, some would be tilted down, some would be tilted sideways. But they are not. They share a common orientation in space, a collective bias that points to a shared and powerful gravitational influence. This is the first major clue that something else is out there, something massive enough to lift these entire orbits and twist them into alignment over billions of years. The second clue is even more peculiar. It has to do with the shape and direction of their orbits. These ETNOs have extremely elongated or eccentric orbits. They swing very close to the Sun, and then travel incredibly far away. The point of closest approach is called the perihelion. In a normal, stable system, you would expect the perihelia of these objects to be scattered all around the Sun, like the spokes of a wheel. Instead, astronomers found that their perihelia are all clustered together on one side of the solar system. It's as if they are all trying to avoid one particular region of space. This clustering, known as the argument of perihelion, is perhaps the most compelling piece of evidence. It suggests that a massive planet is circling the Sun on an opposing orbit, effectively pushing the perihelia of these smaller bodies away. Imagine a large bully patrolling one side of a playground. The smaller children would likely all congregate on the opposite side to stay out of the bully's way. This is what we think is happening at the edge of our solar system. The gravity of Planet 9 is sculpting the orbits of these smaller worlds, shepherding them into these strange, aligned configurations as a testament to its unseen presence. Finding a planet that you cannot see is one of the greatest challenges in modern astronomy. It is a hunt for a needle in a cosmic haystack. Planet 9, if it exists, is incredibly far away. Its predicted orbit would take it hundreds of times farther from the Sun than Earth, perhaps as far as 1,000 astronomical units. At such a vast distance, it would be phenomenally faint. The sunlight that reaches it would be thousands of times weaker than the light that reaches Neptune. And the light it reflects back towards our telescopes would be fainter still, a mere glimmer against the infinite blackness of space. The primary method for finding such a world is through meticulous observation. Astronomers use powerful telescopes, Subaru telescope in Hawaii, Dark Energy Survey in Chile to take deep images of the sky. They photograph the same patch of space over and over again, separated by hours or days. They then use sophisticated computer algorithms to compare these images, looking for any tiny point of light that has moved against the fixed background of distant stars and galaxies. Anything that moves is likely to be an object within our solar system. Most of these will be known asteroids or comets, but somewhere in that data there might be a slow-moving dot that is Planet 9. This is painstaking work. The sky is enormous, and Planet 9 could be anywhere along its vast predicted orbit. It is like searching a vast ocean for a single dark submarine. To narrow down the search area, astronomers rely on computer simulations. They create virtual models of the solar system and insert a hypothetical Planet 9 with a certain mass and orbit. Then they run the simulation forward for billions of years to see if this virtual planet produces the same kind of clustering of icy objects that we observe in reality. By testing thousands of different possibilities, they can constrain where the planet is most likely to be. These simulations are the treasure maps that guide the observational astronomers. They can tell us which regions of the sky are the most promising places to look. For example, the models suggest that Planet 9 is likely at its farthest point from the Sun right now, making it move very slowly and appear even fainter than usual. This makes the search incredibly difficult, but not impossible. Every night telescopes scan the heavens, and every day computers sift through mountains of data. The hunt is on, a silent, patient vigil for a world whose existence is written in mathematics but has not yet been captured in light. The search for Planet 9 is, honestly, a beautiful marriage of two powerful scientific tools: observation, theory. On one hand, you have the brute force method of sky surveys. Telescopes with huge mirrors and sensitive digital cameras are charting the sky with unprecedented detail. Projects like the Vera C. Rubin Observatory, soon to come online in Chile, will revolutionize this search. It will, repeatedly image the entire southern sky every few nights, creating a deep time-lapse movie of the universe. Its ability to detect faint moving objects will be unparalleled, making it perhaps our best hope for directly spotting Planet 9. This direct detection method is fundamentally simple. You are looking for a dot that moves, but the scale of the task is, well, monumental. The amount of data these surveys produce is staggering, far too much for humans to analyze alone. This is where artificial intelligence and machine learning come in. Scientists are training algorithms to be expert planet hunters, teaching them to recognize the subtle signature of a slow-moving object hidden in a sea of cosmic noise. This fusion of big glass and big data represents the cutting edge of astronomical discovery, a high-tech dragnet sweeping the celestial sphere for our missing world. While the observers scan the skies, the theorists continue to refine their models. The discovery of every new extreme trans-Neptunian object provides another precious data point. Each new orbit can be fed into the computer simulations, helping to either strengthen or weaken the case for Planet 9. If a new object is found with an orbit that fits the predicted pattern, the theory gains strength. If an object is found that defies the pattern, the theorists must go back to the drawing board and adjust their models. It is a constant dialogue between the sky and the computer. This process is a perfect example of the scientific method in action. It is a cycle of hypothesis, prediction, and verification. The hypothesis is the existence of Planet 9. The predictions are the specific orbits and locations derived from the simulations, and the verification comes from the telescopes, which are tasked with finding the evidence to confirm or deny the theory. It is a slow, methodical, and often frustrating process, but it is driven by a deep and powerful curiosity to understand the true nature of our solar system, to complete our map of home, no matter how far we have to look. If Planet 9 is truly out there, what kind of world is it? The gravitational evidence suggests it's a giant, with a mass somewhere between 5 and 10 times that of Earth. This places it in a fascinating category of planet that we just don't have in our inner solar system. A super-Earth, a mini-Neptune. These are actually the most common types of planets we've found orbiting other stars in our galaxy, yet we don't have one of our own. The discovery of Planet 9 would mean that our solar system is not so unusual after all. It would be our very own super-Earth. A cold and lonely one, but one that connects us to the broader galactic family of planets. So, where did it come from? The leading theory is that Planet 9 is a native of our solar system, a planet that formed alongside Jupiter, Saturn, Uranus, Neptune. In the chaotic early days of our system's history, the space between the giant planets was a wild and crowded place. It's possible that a fifth giant planet core formed there, but it was kicked out into a distant, eccentric orbit during a gravitational scuffle with Jupiter or Saturn. In this scenario, Planet 9 is a lost sibling, an exile cast out from the bright heart of the solar system, to wander forever in the frozen darkness. Its composition would likely be similar to that of Uranus and Neptune. It would be an ice giant, a world with a small rocky core surrounded by a thick mantle of water ices, ammonia ices, methane ices. Above this would be a deep atmosphere of hydrogen and helium. Being so far from the sun, its surface temperature would be incredibly cold, likely around -230 degrees Celsius. It would be a dark, frigid world, receiving only a tiny fraction of the sunlight that we do. It would be a planet defined not by light and warmth, but by immense cold and the crushing pressure of its own gravity. The existence of such a world would solve one mystery, the strange orbits of the Etienneaus, but it would open up so many more. How did it get kicked out so far? Why did its orbit stabilize where it did? Could it have moons of its own? These are questions that would ignite a new era of planetary science. Finding Planet 9 would be like discovering a new continent on Earth. It would be a completely new type of world in our own backyard, a laboratory for studying planetary formation and dynamics in a regime of extreme cold and distance that we have never been able to explore before. While a rogue ice giant is the leading contender, there are other more exotic possibilities for what Planet 9 could be. One of the most mind-bending ideas is that it isn't a planet at all. Instead, it could be a primordial black hole. These are not the familiar black holes formed from the collapse of massive stars. Primordial black holes are hypothetical objects that are thought to have formed in the first fractions of a second after the Big Bang, when the universe was incredibly dense. Some of these tiny ancient black holes, perhaps only the size of a grapefruit but with the mass of a planet, could still be wandering the galaxy today. It is a stunning thought. A relic from the dawn of time itself could have been captured by our sun's gravity, and now be silently orbiting in the darkness. From a purely gravitational standpoint, a 5 Earth-mass black hole would have the exact same effect on the distant Kuiper Belt objects as a 5 Earth-mass planet. We wouldn't be able to tell the difference just by looking at the orbits of the Etienneaus. The gravitational pull is identical. Finding such an object would be a discovery of monumental, perhaps even revolutionary, importance for physics and cosmology. It would be the first evidence that primordial black holes are real. How could we ever tell the difference between a planet and a black hole? It would be incredibly difficult. A primordial black hole would be completely invisible, as it emits no light of its own. However, it might be possible to detect it through other means. If a small comet or asteroid were to pass very close to it, the object would be torn apart by the intense gravity, producing a brief, faint flare of radiation that our telescopes might be able to see. Another, more futuristic method would be to send a fleet of tiny fast-moving probes towards its predicted location and see if their trajectories are bent by its gravity. This idea, while speculative, highlights the profound nature of the search. We are probing a region of space so dark and so distant that our assumptions about what we might find are constantly being challenged. The object causing these gravitational ripples could be a planet, which would be amazing, or it could be something far stranger, a piece of the early universe captured in our own backyard. Whatever the answer, the pursuit forces us to be open-minded and to consider possibilities that stretch the very limits of our imagination. The mystery of Planet 9 is not just about our solar system, it's about the fundamental nature of the cosmos itself. We must also confront another possibility, one that is perhaps less exciting but equally important from a scientific perspective. It is the possibility that there is no Planet 9 at all. The strange clustering of the distant icy worlds might not be real. It could be the result of observational bias. The regions of the sky we have surveyed most deeply are not uniform. We tend to point our telescopes where it is easiest to look, away from the crowded plain of the Milky Way, for instance. It is possible that we have only found the ETNOs that happen to be in these well-observed patches of sky, creating the illusion of a cluster. Think of it like a person fishing in a lake but only casting their line into one small cove. If they catch all their fish in that one spot, they might conclude that all the fish in the lake live in that cove. But the real reason is simply that it's the only place they have looked. Some astronomers argue that this is what has happened with the search for ETNOs. We have found a handful of objects that happen to align, but as we survey more of the sky, we will find others that are scattered randomly and the pattern will disappear. The ghost will vanish because it was never really there. This is a healthy and necessary part of the scientific process. Every bold theory needs to be met with rigorous skepticism. The claim that there is a giant planet hiding in our solar system is an extraordinary one, and it requires extraordinary evidence. So far, the evidence is compelling, but it is also circumstantial and based on a very small number of objects. As our telescopes get more powerful and our surveys more complete, we will find hundreds, perhaps thousands more of these distant worlds. This new data will be the ultimate judge. If the pattern of clustering holds up as we find more and more objects, the case for Planet 9 will become almost undeniable. But if the pattern dissolves and the new objects are found to have random orbits, then the theory will have to be abandoned. Science is not about clinging to ideas we like. It's about following the evidence wherever it leads. Even if Planet 9 turns out to be a phantom, the search itself will have been incredibly valuable. It has pushed us to develop new technologies and survey the outer solar system in more detail than ever before, revealing a treasure trove of new dwarf planets and icy worlds in the process. Let us imagine for a moment that the search is successful. One day, an astronomer looking at a new set of images sees it, a faint, slow-moving point of light, exactly where the simulations predicted it would be. Follow-up observations confirm its distance and its mass. Planet 9 is real. The discovery would be a moment of profound significance, a cause for global celebration. For the first time in over 170 years, since the discovery of Neptune, our map of the solar system would have a new major planet. School children would learn a new mnemonic. Our perception of our place in the universe would shift. The discovery would instantly transform our understanding of how our solar system formed. It would prove that the early lives of planets are violent and chaotic, a cosmic billiards game where entire worlds can be flung into the abyss. Planet 9 would become a primary target for future exploration. Though sending a probe like New Horizons on a journey that could take decades would be a monumental undertaking, the scientific prize would be irresistible. We would want to see this dark, cold giant up close, to measure its atmosphere, to search for moons, to unlock the secrets of its origin story, but the implications go even deeper. Finding Planet 9 would remind us that we live in a cosmos that is still full of surprises, even in our own neighborhood. It would show that there are still great discoveries to be made, that the age of exploration is far from over. It would underscore the power of the human mind to comprehend the universe, to infer the existence of a hidden world through logic and mathematics before ever seeing it with our own eyes. It is a testament to our relentless curiosity, our innate desire to look up at the sky and wonder what is out there, whether Planet 9 is a rogue ice giant, a primordial black hole, or simply a ghost in the data. The quest to find it has already enriched our view of the cosmos. It has forced us to look deeper into the darkness than ever before, and to grapple with the grand story of our own origins. It reminds us that our sunlit world is just one small part of a much larger, colder, and more mysterious system. And it leaves us with a beautiful, humbling thought, that even after centuries of astronomy, our map of home is still not complete. There are still new worlds waiting to be found.